Hi, welcome back to the Cuzzy Sound channel. My video on the Inline Attenuator got some nice comments, thank you for those, it's always great to get feedback. And in amongst those comments, Bert asked, does it matter which end you use as the input? Well, that got me to thinking. There's two ways to look at this. One is, what does the theory say? But more importantly, what happens in practice? Does it actually make a difference if you plug it in the opposite way around? So I decided that rather than just try and type some response up to Bert, I'd make another video because other people might be thinking the same thing. So in this video, I'm going to first look at the theory behind the voltage divider stroke attenuator circuit, but I'm going to do that at a fairly high level, so it won't be academic. You won't be passing the exams with what I'm going to tell you. You could do what I did, and that is go and research it. There's plenty of people out there who know a lot more than me and explain it rather well in detail. So I'm going to give you more of a broad overview, and just so that you get a feel for where the circuit theory comes from. But then, which is probably more important to people like me who basically just want to get on and make some electronic music, what happens in practice if I just get all of this and literally just turn it round and plug it in the other way around. So we'll try that as well, and we'll try and show you. I've got the oscilloscope running so we can see what's happening on the scope, and we'll be able to hear it through the audio as well. So okay, it's back to school. We will start by looking at a basic voltage divider circuit, and the simplest way to do this is to have two resistors. We've got R1 and R2. We have the source voltage coming in at one end of R1, the opposite end of R2 is connected to ground, the two resistors are connected together in the middle, and we take a centre tap for our divided output voltage. Now the first theory we can apply to this kind of circuit is Kirchhoff's voltage law. So what this law says is that there will be a voltage across R1, there will be a voltage across R2, so we'll call those V1 and V2 respectively, and because the same current is flowing through both resistors, we know that the source voltage is got to equal the sum of the voltages across the two resistors, V1 and V2. Now we're talking resistors, volts, so resistance, volts, voltage and current. I'll get this right. So the next law we can apply when we've got VI and R is Ohm's law. So we've still got our very simple circuit, and what Ohm's law says is that the voltage at the output will be equal to the source voltage times the value for R2 over R1 plus R2. Let's stick some numbers into this and give you a worked example. So if we assume that our supply voltage is 9 volts, R2 has a value of 27 kilo ohms, 27k, R1 is 22k ohms. Put those numbers into our equation, so the output voltage should be equal to 9, the input voltage, times 27 over 22 plus 27. The k's cancel out. So if you do that calculation, you find that the output voltage is 5 volts. If rounded up to a whole number, it's actually 4.9 something or other. But there you go. So using that simple voltage divider circuit, we can take a 9 volt input and end up with a 5 volt output. can sometimes be very useful, and I've used that circuit in other designs that I've built. If we replace our two resistors with the potentiometer, so now we've got the circuit that I actually built in my simple inline attenuator, what we're actually ending up doing is that the total resistance of the potentiometer, RT, that's the value that's written on the potentiometer, is equivalent to what we had in the other equation as R1 plus R2. It's the two resistances added together. And then the output would be where the resistance at the wiper, which is essentially what our R2 resistance was when we had the discrete resistors. So the Ohm's law equation would now look like what we've got on the right here, in that the output voltage is equal to the source voltage times the resistance at the wiper divided by the total resistance of the potentiometer. There we go. That is pretty much the basic theory of the simplest voltage divider. If you want it in more detail and you want to see the working out that goes between Kirchhoff's law and something that looks like this, there's lots of people out there who have posted things on the net, and they know a hell of a lot more about this than I do, and they show you how to derive the equations. So if you want the detail, go for it. In terms of a basic understanding of what's happening with the circuit, well, this is the basic understanding. If we now consider that same circuit as an attenuator, we're into a whole new world of values and units, and we start to talk about things like impedance matching, which is one of the reasons for using an attenuator. So if we've got an impedance mismatch between the input and the output, we can use an attenuator to help match that impedance. It will attenuate the signal, so it's still working a little bit like a voltage divider, although when we start talking about attenuation, they often start using values in decibels, so we're now into logarithmic calculations. If you want that theory, go and look that one up. That gets a lot more complicated, and I'm not going to go into it here. But if we look at our circuit, now it says it's unbalanced. If we had another resistor on this side here, that would be a balanced T pad attenuator. Fixed attenuators like this are called pads. But no, we have the unbalanced one. Now if you go the balanced one, then it would impedance match in both directions, so it wouldn't matter which way around you put it in the circuit. In this case, you will only get your impedance match if it is arranged such that the input is on this side and the load that you're matching the impedance to is on this side. But if we look at this in terms of a signal going in and a signal coming out, and we're not too worried about all this impedance matching and dB and things, in theory it shouldn't matter which direction your current is flowing and which way the signal's going in. What should matter is what proportion of it is dropped down to earth through this resistor, and what proportion of it is allowed through this resistor. So provided you're not too worried about the impedance matching and things, it would appear that to answer the question, in theory, it shouldn't matter which way around you plug your inline attenuator into your analog synth system. You will get pretty much the same kind of effect, so long as we're not too worried about impedance. Well, that's the theory anyway. Here we have our inline attenuator set up on the synth. I've got output coming from, it's the triangle wave on the 3340 going into the in on the attenuator. The out on the attenuator is going into one of the Starfish multi-plug things. The reason it's doing that is so I can take one output into the mixer so you can hear what's happening, and the other output is going into the oscilloscope, so if we watch the trace on the oscilloscope as well as hear what's happening. So this is with the input going on the side that's labelled in. So this is the side that where it on the, if you looked on the theory, where VS was the source, that's what the signal's going into, and then what was the wiper on the pot, that's what the signal's coming out of. So if I now move the position of the wiper, you should hear the volume of the signal change, and you should see the amplitude on the oscilloscope trace change. So I turn it up, and back down again. So there, I'm at around about 0.2 something volts, 0.5, 0.8, and at maximum just below 1.8, 1.78 I think it's peaking at there. Okay, let's do some hot plugging again like we did last time round. This time round I'm going to take the input out, take the output out, and then literally turn it round. So the input is now going on the side marked out, so that's coming from the oscillator, and the output coming from the side marked in. And we are still reading 1.78 volts, and if I turn it down, so, as a practical demonstration of it literally controlling the amplitude, i.e. the volume of the signal coming out of the oscilloscope, the oscillator through the oscilloscope, yeah, the answer to your question, Bert, is no. It doesn't matter which way around you connect it. In this configuration, it works both ways in pretty much the same way. Well, that was a simple and probably not very scientific experiment, but it did serve to answer the question, does it matter which end you plug the input into? And it appears, certainly on my system and the way I used it there, that no, it doesn't. You get the same kind of volume or amplitude or voltage adjustment regardless of which way round you plug it in. So hopefully I've answered the question that was posed in some way or another. What I will say is that if you're going to start and play around with these things on your own kit, then please be careful, particularly if you're plugging things into commercial gear. Be sure that the voltages that you are playing with are not going to exceed the manufacturer's recommended limits. I wouldn't want you to start playing around based on something that I've done and suddenly find that you've got smoke pouring out of the back of your expensive gear. So please, if you're not sure, don't start plugging things in randomly. If you can, then check what the limits are, make sure that you're operating within the limits. Provided you're operating within the limits, then experiment and explore a little bit. Who knows what you might find. Thanks for watching. Hope this has been helpful. Catch you next time.